Hello, everyone. Let's start. Today, we will talk about the assembly language. Assembly language is a interface between the instruction set of your computer and the compiler. So all the compiler will, compile or translate your program written by some high-level language like C++ or Python, or nowadays it's Rust or Ruby language into some instruction um, um, belongs to the instruction set. And most compiler will translate those languages into assembly language first. And then after some optimization happens on the assembly language, these optimized assembly language will be translated to the instructions, which can be executed by your machines. So this figure indicated this structure. So now all the high-level language, Java, C, will be translated into assembly language. And then we have a lightweight compiler, which will translate the assembly language to the machine code. Each line of the machine code indicate one instructions. So these binary bits, one line can be one-to-one mapped to this assembly language code. And then your computer can process these binary machine code. And your operating system is on the top of the whole thing. So these part should be independent from the operating system. So on Windows or Linux, you can have the same assembly language. You can use the same assembly language to do the programming. They will be translated into the same machine code. Assume that you are using x86. So the operating system is not important here. So because assembly language is very difficult, nowadays most user use the C to write their applications, or even higher level language to write their applications. And then we can use some C compiler or assembler to do the translation. And then we have the binary bits, which can be processed by your CPU. Nowadays, these compiler get complicated, like CUDA or OpenCL. Those compilers can support not only CPU, but also GPU and other accelerators. But each piece of hardware can be programmed by assembly languages, because assembly language is the interface between your hardware and your software. If you now, people talk about the portability a lot. The so-called portability is that when you write the same applications by, let's say, by Java or C, can you directly compile code on Intel CPUs and compile your code on ARM CPUs? The short answer is yes. You can achieve that by using different compilers. But again, in order to support this portability, you need to heavily optimize your code and use the right compilers. Because different CPU have different instructions. So the same sentence in the C language will be translated into different binary codes or instructions on different CPUs, like this. So even on the same x86 instruction set, you have different versions of CPU. Even from the same company, you can get different versions of core CPUs. So they may not, be compatible with each other. For example, some old CPU like Pentium, they do not support a new instruction set like AVX 512. So AVX 512 is a new instruction, multiple new instructions that can support single instruction multiple data processing in the latest Intel CPUs. So from this perspective, the difference between the old Intel CPU and the new Intel CPU is even larger than the difference between the latest Intel CPU and the latest ARM core. So providing this portability is very difficult, but it's still doable. And the instruction set can, defines the system state by register, memory, or program counters. One example of the system state is that which application you are executing now. As we know that one CPU can support multiple applications. And of course, the instruction set can define the instruction one CPU can process. And the effect that each of these instructions will have on the system state. So by one instruction, you can switch to another applications. Or by one jump instruction, you can jump to another basic block or another loop of your code. So there are two types of instruction set. One is a so-called complex instruction set. The other one is a reduced instruction set. The complex instruction set is built upon the philosophy that each operation needs a single instruction. So you may have very powerful instruction like the square function. The square function maybe is implemented by dedicated instructions. So from this point of view, the CISC, so-called CISC instruction set is very powerful because each instruction can implement very complicated functions or complex functions. The other is called RISC, which is so-called a reduced instruction set. Well, the RISC design philosophy is that each instruction is very weak. Each RISC instruction cannot do too much. Maybe this square function will be translated to several load instructions, one multiply instructions. You need to break this square function into multiple instructions in the RISC structure. But again, because first, you have only several elementary instructions. So it's very easy to accelerate these elementary instructions. You can set the same length um, for all the instructions here. So in this sense, um, it's easy to implement a pipeline on this instruction set. Um, and also it's easy to achieve higher frequency uh, from this perspective. The higher frequency means it's very easy for the RISC to achieve 2G or even 4G hertz. Um, Although each instruction is weak, um, the frequency is high. So you can use maybe 5 instructions to form a complex function. But nowadays, the powerful CPU are all CISC design. For example, your Intel CPU. At least at the server level, laptop level, people need a CISC design. But for your mobile phone, for small IoT, Internet of Things devices, people like RISC design. There is also a trend where somehow they are merged. Why? Because in order to achieve higher frequency, Intel designed a so-called microcode. Microcode is a abstract layer under the instruction set. So in order to provide you the compatibility of x86, Intel company cannot, easily change their instruction set. Otherwise, originally my code used these many instructions of x86. If you change them, if you remove them, I cannot use my code on your new CPU. This is not good. They will lose a lot of customers. In order to maintain the same instruction set, they actually add another abstract layer where they translate their instructions to that so-called microcodes. The microcodes is somehow a RISC design. So in this way, they can achieve very high frequency at that microcode level. So each instruction will be decoded, will be fetched, decoded so that the CPU can understand the content, the function of this instruction. And of course, they are stored in the main memory. So somehow they are data. They are also data. The registers can help the ALU to temporarily store some intermediate results. And then we have the more data in the memory, in the DRAM. So somehow we need a different method to address, to index each memory object. So these are famous CPU companies like the Intel, ARM, MIPS. MIPS is another type of RISC CPU, which is the same as the ARM CPU. But again, the performance of MIPS is very weak. So they typically only used in the printer or some game consoles. Nowadays, I think even game console require higher performance AMD CPU maybe. So the ARM CPU is heavily in your mobile phone or your iPad. Nowadays, people push ARM CPU to higher level computing platform like personal laptop. I think the latest um, Apple laptop is built based on the ARM core. So each company has their own instruction set, although these two both belong to the RISC instruction set, but their instruction set are totally different. I think the ARM use some instruction set, while MIPS has their own instruction set. But these instruction set can be, grouped into CISC or RISC. Now, even for the same instruction set, like Intel, they have different microarchitectures. What does this microarchitecture mean? Microarchitecture means the size of your cache. How many branch predictor do you have? Whether this your cache adopt write back policy or LRU replacement policy. These details can be summarized as the so-called microarchitecture. So in this sense, let's say the Pentium 4 Intel CPU has totally different microarchitecture compared to the latest iCore 7, but they both from Intel. So these are the features of microarchitecture. The number of registers, how many registers does one CPU have? Is it a microarchitecture? Yes, this belongs to a microarchitecture. How about the CPU frequency? No, this is not a microarchitecture because one CPU can potentially operate it at a different frequency, 1G or 2G hertz. Sometimes the Intel intentionally reduce the frequency of some CPU so that it can be used in the low power scenario. The memory size is not your microarchitecture. Cache size, if I ask you whether cache size is a microarchitecture, the answer is no. Why? Because only the L1 cache size is a part of the microarchitecture, while the last level cache size is not. Because in different CPU core, people use different last level caches, even on the same, like Pentium 4, because they needed to customize the last level cache for server CPU or average user CPUs. So when you try to write programming, when you try to write assembly language, you need to understand your microarchitecture because you need to address all the registers. So this is why it's very difficult to write a programming language nowadays anymore, because it's heavily depend on the microarchitecture. So when you write some programming language, these many structures can be known. For example, the program counter. And of course, the registers. So one very simple sentence is like for I from 0 to I smaller than 256. And then we iterate the loop. These single sentences will be translated to at least 4 or 5 assembly programming language sentences because you need to use different registers. And also you need to use these condition codes to evaluate whether you reached the array limit or not. And also you need to manipulate the memory heap and the memory stack. In order to manipulate the memory object, you need to understand the size of your data. For example, what's the size value of your integer? Whether your CPU support 128-bit integer. You need to know all these details. That's the reason why directly programming assembly language is difficult. Typically, we write C and then use the GCC or ICC to translate the code into assembly language. So in order to support the assembly language programming, one CPU provides different types of registers. A register is a storage which can be accessed very fast, typically 1 cycle latency. So in assembly language, we can use this symbol to indicate, okay, this is a register. And each register has its own dedicated name. Register is the most important part in the assembly language. So here is one example. Because now we have a 64-bit machine. So each instruction is a 64-bit. 64-bit is of course 8 byte. In order to access the lower order of this 4-byte, we have another name for this part. Actually, these two are pointing to the same register. The only difference is that this name indicated the entire 8-byte register, but this name is used for only the lower order 4-byte register. So this is the name. This is the difference between the memory and the registers. So in memory does not have a name. It has only addresses. On the contrary, register has its name. The capacity, of course, is different. Access speed is different. They implemented by different types of memories. We talk about this in the cache part. So in the modern assembly language, we need to clearly write some instructions to enable some data transfer between the register and the memory system. This is particularly true for the RISC machine. So you need to implement a load operation by this sentence. This is the register name. This is the memory address. So by doing this, you can load the name from the memory to the register files. This is a store operation. After your data, your operand are stored in the register, you can perform the logical or arithmetic operations. And then you can also have some conditional flow like jump or conditional branches. For the operand, we have different types. We have so-called intermediate operand, which is actually the constant number. When you want to perform this one is a intermediate. Immediate number. And this number will be stored in its dedicated register. And we have so-called integer registers. And in the x86 machine, we actually have 16 such registers. These are two examples. And this one is reserved for some other use. So the memory addresses can be also stored in the registers. So you can use this register to store the first element of a memory array. The move instruction can help you enable the data transfer between the register between registers and between the register and the memory. So here is one example. You can add different letters at the end of this move instruction. B indicates 1 byte, W indicates 2 byte. W is indicator a word, which is a 2 byte. So the first operand is the source. The second one is a destination. You actually move the data from here to here. And here are some examples of the arithmetic operations. This is addition. This is subtraction. This is multiplication. And then we have different types of shift XOR operation. The first operand is a source. The second one is destination. And the destination is used to, at the very beginning, it is used to store one operand. At the end of the operation, it is used to store the results. So we will translate each instruction here into this form. This is one example. So which means that the results of source the value of source will be added on this destination. And of course, the destination register will have some value at the beginning of the computation. So how can you implement this? So this one will be translated into two instructions. The first one is R1 plus equals to R2. And then the results will be stored in R1. So we will move the results from R1 to R3. So one simple C code will be translated into two lines of assembly code. We also have some instructions which has only one operand. And this is how we can implement a function. For the function, we have some dedicated registers. First, these sentences will be translated into assembly codes. I'm sorry, will be translated into some intermediate representations. And then the intermediate representations will be translated to the assembly code. So in order to support this function, we have some dedicated registers. These dedicated registers can store, this one is can store the first argument of the function. This one can store the second argument of the function. And this return results will be stored in this one. The so-called return is that you store this value to this register, and then the next, the guy who invoked this instruction will read the result from this register. So in this way, you can, return this value to the outside of this function. This is one example of how to implement a swap operation. A swap operation is, exchange the value of two variables. First, because this one can store the first argument of the function, which is xp. This one can store the second argument of this function, which is yp. So this yp and xp are actually two pointers pointing to the memory location. And then we can use the two new variable, which are also two registers to store them, and then exchange them. So here is the details of this example. So the memory data here will be stored to this variable, and the memory value here will be stored in this variable. And then this value will be right back to this memory location, and this value will be right back to this memory location. So in this way, we can actually complete the swapping operation. So we can index the memory by two different methods. The first one is a direct one. So you can easily store the memory location in some register. This is the register. And then you can use the memory, index the memory like this by this symbol. For example, you can write some sentences like this. This sentence means you move the data in this memory location to these registers. So this is a memory location. Why? Because you have this symbol. If you have this symbol, this is a memory location. And what location is the data stored? So the memory address is actually stored in these registers. So this is so-called an indirect index. So you actually store the memory location in some register. It's just like a pointer. And we can also have a displacement. Displacement means you can add a D here. Again, this is very typical case in the C language too. You can write the displacement here. So in this way, we can use this value, the value stored in this register plus this 8. And then we can read that address. This value plus this 8, we can read the value on that address and store the data to this register. So the complete format can be written like this. This is the displacement. This is the base register. This is the index register. And this is the scale factor. And then this is the real memory address we want to access. The index register can iterate one loop from a 1 to any number. And then you can use a scale factor to control how many positions each time you iterate. If this is 2, then you jump 2 positions to the next one. Skip 1 and jump to the second one. And here are some special cases. The so-called special cases is you have only part of the variables here. So typically, if you do not have that part can be viewed as a 0. For example, if you do not have this D, then D is a 0. So in this way, we can compute the address here. We only have a D here, so we can use the address in this register, which is this one, and add this D to compute the new memory address. So you can try the following after this class. We have another powerful instruction named load effective address to help you to manipulate the memory object. Again, the source is the starting point. The destination is also a register. Is the register will eventually store your results. So the destination will be set to the address computed by the source expression. So you can use this instruction like this. So by this expression, we can compute it and get a memory address, and we will store the memory address to this register. We don't need to read the memory from that address, but we just directly write the memory address to this register. For example, we can compute the address without a memory access or a memory reference. We actually store the pointer to this P. We calculate the address and store the pointer to this P. We can also, compute this arithmetic expression and store the value into the destination register, because this arithmetic expression is actually the complete memory addresses. So here is one example of the how to distinguish the lead and the move. So we have a consecutive memory here. They have a consecutive memory address like this. And then we have some values stored in the memories here. So the first instruction is a lead instruction, which can compute the value of this and store this one to the register here. Because RDX is a 4 here, RCX is a 100 here, and we have another 4 here. By computing this, we will know that the RAS will be 110. If we have a move instruction, we need to read the data from 110. read this piece of this data. The value of this piece of data is 8 to here. So we move the data to RBX. Now the RBX stores 0. So for this one just read the value of the value of this register. The value of this register is 100 to this register. And this move, the difference between Li and move is that move actually read the data in the main memory to the register files. So what does it mean? So since RDX stores 110, so the move needed to actually read the data at a 110 address and back to this register. So it's just a 1 here. Any question? So in this lecture, we just briefly introduced the assembly language. Besides the assembly language, I need you to help me to complete the OCQ. Your feedback will be, heavily considered, will be greatly appreciated. Thank you very much. And the next lecture, we will have the final presentation. And in order to better evaluate everyone, I plan to incorporate other students, the feedback of other students in the same class. So you can actually rate, the project of other students. You can email me your evaluation after the class. I would like to encourage students to do the presentation first. So do not, delay it to the next, to the class after the next class. Just, try to do the presentation next class. So if you have any concern, any difficulty, we can talk in the final presentation. Any question? So if no question, we can stop today. If you still have some private question, you can email me. Thank you very much. Thank you.
Thank you.